Hello, I'm here to present to you SP14 Green's Chess AI project. Our group is Hakeem, Cody, Nathan, and Oleg. Our plan for this project was to create a chess game that is both functional and also accessible for people of any skill level when it comes to chess, whether you're brand new or whether you're very experienced. We wanted to have player versus player functionality for local games. We also wanted to have a player versus AI game mode, and then we also wanted to have board customization options so that players can choose different board themes just to make it a little bit more customizable and a little bit more interactive of an experience for the user. So our requirements for this project that we are specifying is that the game board has to be interactive, which means that it has to have drag and drop capabilities. When a piece is picked up, it can be moved to a legal square, but not an illegal square, and that goes right into the game rules compliance. The game has to enforce the rules of chess, the very common ones like checks, stalemates, and captures, but also some of the more rare ones like threefold repetition and some of the more extraneous game rules. We also want to have an AI that understands the possible moves that it can make and selects a move that makes sense for the given state of the game. And it also must adhere to the game rules and return moves at the proper time. And we want it to be very maintainable, which means we want it to have well-structured code, well-documented, easy to read, easy to understand. And for our version control on this project, we are using GitHub. So some of the assumptions that we have for this project are that players in AI only can make legal moves. The game also enforces this to a certain extent, so that a player wouldn't be allowed to make a move that is illegal. But just for the player experience, the experience will be much better for the player if they are aware of legal moves that they can make and are mostly only attempting to make those. And that goes into the players understanding the basics of chess. Our platform is not very instructive. It is much more focused on allowing players the space to play the game. So players, an assumption is that players are coming into this with some knowledge about chess so that they can play on their own. Another assumption is that all games conclude with win, loss, or draw. That is just a feature of chess, and that's one of the assumptions that our chess platform is running on. And then also the positions of all pieces will be tracked and updated after each move, and I'll talk about how that's done in a second. So for the layout of our game, we're using Figma as a mock-up, and it's a very simple and direct user interface meant to just get players straight into the game, be pretty intuitive and easy to understand. That way any type of player can come and understand what's going on very easily. And the functionality is very general. It's intuitive, it's easy to understand. Players are going to be able to see what the buttons say and understand what their options are. So for the design of our system, we wanted to have different color palettes for the user to select between. These are just some examples. We ended up not going with these exact colors, but we wanted it to have some user customizability so that they could make it feel a little bit more interactive. And then we also want there to be a way that the legal moves are displayed to the user when they are dragging a piece. When I was talking about the drag and drop functionality earlier, it ties in with that to where when a player is dragging a piece, the legal moves that piece can make are displayed on the board, and that'll make it a little bit easier for newer players who, even if they don't have a full knowledge of chess like our assumption said, they'll still be able to figure out what's going on to a certain extent, because the legal moves that the piece that they're dragging can make will be displayed to them. So I'll talk for a second about our software development strategy. For developing this project, we tried to adhere to the software development lifecycle, meaning that we started out our project development by planning, specifying our specifications, or laying out our specifications, our requirements, and then our purpose for the project. So that way, when we went into the design part of it, we knew what we wanted and we knew what we needed to get to. So then we spent some time designing how it would function, how it would be cohesive, and what components we would need for the system. So that way, for the implementation part of it, we already had a lot of that designed and planned beforehand. So we just implemented that in the way that we specified in the design part, and then we just rigorously tested all components of our system to make sure that, one, that they were functional and that they didn't cause errors or lead to undesired system responses, but then also that we tested to make sure that we met all of our initial specifications that we laid out at the beginning, that our system responded in a way that meets those specifications. Okay, so I'll talk a little bit about how the actual game is run for the actual platform itself. So this is for the chess game that you interact with. In order to implement the chess game itself, we went ahead and used Python's Python chess library, and that gives us access to a lot of different objects and methods that made it a lot easier to handle the inputs that come along with a chess game. That includes a board object, and what you see here at the bottom of the screen is what happens when you just print a board object. You can see an ASCII depiction of what the game board is, and that's used for updating the game state. When it's updated, this board.piecemap method is what you see on the right. When you print that, it has some very useful information when it comes to where pieces are on the board, and that can be used to that was used to help know what the game state was at, where the game is at, and it can help update that. And then also a very useful tool that came along with the Python chess library was the board.legalMoves method, or it's an attribute, and that gives you a list that contains all of the legal moves that can be made in a given position, and you can limit that to the legal moves that can be made for one side of the board, and that's how you can check that the moves that the users are making are legal moves, and that way it can decide whether to try to play those moves or to make the user pick a new move, and that way it handles a lot of that checking for us. Okay, so now let's talk about some of the classes and objects that we use to get this system to work. The biggest and overarching class that a lot of the game state and game updating was done was in this board class that you see on your left. It has, you can see the example of how it initializes itself. It both contains in this self.board pos attribute, it contains the Python chess object for a game board like you saw in the previous slide, but then it also contains a bunch of other useful attributes that are just good for updating the actual user interactive part of the chessboard after each move, like whether the board needs to be flipped or not, or and it also contains a grid of square objects, which allows for determining which square is clicked by the user. Python chess has classes for how to display board objects and stuff like that, but we didn't want to use the Python chess ones because it basically locks you into a very narrow, a very narrow possibility, or very narrow creativity for what you can create. So we went ahead and did ours custom, and then on the right you can see the square class. The board object is made up of 64 square objects, and these square objects contain their position, their index, and then a lot of other things that have to determine what color they are, where they're drawn, all these things, and that allows for when the user makes a click, it can determine which square is clicked, and then which square the piece is moved to, and then it can determine whether that move is legal for the board, and then it'll play it on the board and update the board. And so that kind of goes into, for the Python implementation of the actual game part of the chess system, we used Pygame in order to deal with event handling and click handling and those kinds of things. On the top right, that's what you see is just an example, one of the examples of a mouse button down event handle that we did. And basically that just allowed us to have a continuous game that is cohesive, so that it allows you to navigate between all possible windows, all possible menu screens and everything like that, and it allows you to continue looping through that. And then it also allows for the user to interact easily with the system in a way that's a lot smoother than doing it otherwise. And then at the bottom is what you see with the move handling. So when the user clicks on a piece on the board and drags it, the first thing that it does when you click is that it saves the initial square that it starts from. And then when you drag the piece and drop it off on another piece, it saves the square that you dropped it off on. And then it takes those two coordinates and puts them into the make move method, and then that make move method, you can see it does a check in the board.legalMoves attribute that I was talking about earlier. And that way it checks if the move is legal for the board in whatever position it's in, and then if the move is legal, then it plays it on the board and updates the screen so that the move is displayed on the board. But if the move is not legal, then the piece just goes back to its initial starting square and the player has to select a new move. Okay, let's talk about the AI chess engine that we made and how we went about making it. The algorithm that we utilized and implemented for the AI's decision making was a mini-maxing algorithm. And in order to optimize it and make it more efficient, we utilized alpha-beta pruning. And I will explain both of those momentarily. So the idea behind Minimax is a little bit complicated, but basically it comes down to there is one player that is the maximizing player and one player that is the minimizing player. The maximizing player will always select the move out of all possible moves that is of the highest value, and the minimizing player will always select the move out of all possible moves that is of the lowest value, and that is how moves are selected in the AI's best interest. And that's done through post-order traversal of the tree of moves. So when it's the minimizing player's turn, it selects the lowest value move from the tree to go on to the next level, and then when it's the maximizing player's turn, it chooses the highest value. So let's go ahead and see an example of that. So for this first one, we have 2 and 3. These are two moves. One is assigned a value of 2 and one is assigned a value of 3. Since it's White's turn to play, White is the minimizing player. So White's going to select 2. That way 2 moves up to the next level of decision making. And then you see the same is done in the next one. There's a move that's a 1 and there's a move that's a 4. So the 1 is selected, and now it's Black's turn. Black is the maximizing player, so Black is the maximizing player. It's going to select the one of the highest value, so that move of 2 goes all the way up to the top, and that is the move. That is the move path that is selected. So then the question is, if the maximizing player is trying to select the moves of the highest value and the minimizing player is trying to select moves of the lowest value, how are those move values determined? And those move values are determined through a series of principles and weights. Basically, there is a series of principles that we want the AI to follow to make moves that make the most sense in any given position. In order to incentivize the AI to make those moves, we give what we consider good moves a more advantageous value to the AI. So if the AI is the maximizing player, then we make good moves have a higher value, so it's more likely to pick them. We make bad moves have a lower value, so it's less likely to pick them. And those values take a couple different shapes. So one of them is being just strictly material value. When the AI is making its decisions, it takes into account if it's able to take any of the opponent's pieces. And obviously, in the game of chess, taking an opponent's piece is of great significance, and it gives you a big advantage. So those have much higher numbers. The highest, of course, being if you're able to checkmate the king, because that is how the game is won. So that has the highest possible value. But we don't want the AI to just strictly play off of material value for a couple reasons. First of all, you're not always able to take pieces. There's a lot of moves that you have to make in between where you can't take pieces, and you don't want that to just be random. But also, you don't necessarily want to just play off of strictly material value, because that's not how humans play chess, and that's not the best way to play chess. So then a secondary mean of incentivizing the AI to make certain moves is through positional value. Certain pieces are more valuable in different parts of the board than other parts of the board. For example, here on the right, you have a knight. A knight is much more valuable as a piece. It can attack many more squares when it's near the center of the board, and it can attack less squares when it's on the outside of the board. So by adding these weights in this array format that you see here, to where if you see these indices in the arrays as squares on the board, the knight is much less likely to want to move towards those negative values if it's the maximizing player, and it's much more likely to want to move towards the positive values. And those are all, in the end, all the weights are added together to determine what the best move is. So having these slight, small, little positional value changes helps make the AI play a little bit more nuanced. So the idea behind alpha-beta pruning is that it skips unnecessary evaluation of nodes. So if you look at this example below, the first two moves that are being considered are moves of value 2 and 3. And white, as the minimizing player, wants to select the move of the lowest value, meaning that it's most in white's self-interest. So it selects the move that is assigned the value of 2. So then the next pair of moves is considered. The first one is a 1, is assigned a value of 1. So white is the minimizing player, so no matter what, white is going to select the lowest value. But black is the maximizing player, so black is going to want to select, when it's its turn to consider moves, it's going to select the highest value. And those two things combined mean that this next one is always going to be 1 or less. And since that one is always going to be 1 or less, black, as the maximizing player, is going to pick the other option, since it's 2, since it's greater than that. So that being said, we can actually prune this part of the tree off and not consider it. And that way we're skipping some unnecessary evaluation, and thus improving some of our AI's efficiency and improving its performance. And that is a summary of our chess AI methodology, as well as our chess platform creation and our plan in creating it. So now I'll do a quick demonstration of the final product that we've created. Okay, so now let's take a demo of the chess platform and game that we created. So first, this is the main menu. As we described in the plan for it, it's relatively simple, it's easy to understand, and it's very quick to pick up. So let's look at some of the features here. One of the features that we have here is a color menu that opens when you click. Here, it allows you to select between different board themes and colors, and I'll show that in a minute. But we'll go ahead and get into a local game so you can see what that looks like. So when you start a local game, the board is drawn with all of the pieces in the correct squares. When a piece is selected, the legal moves that that piece can make are drawn on the board. So we'll go ahead and start playing some moves. The board flips in between each turn since it's a local game. And when you normally play a game of chess, you're looking at the board from the perspective of your pieces. So we wanted to make it so that when you play a local game, it flips those pieces. And as you can see, no matter what piece you pick up, the legal moves are displayed. We'll go ahead and play a check here against the king. And the king is in check, so this side should only be able to make legal moves that defend the check. And as you can see, it can only play blocking moves. So we'll go ahead and do a checkmate here so you can see what that looks like. Go ahead and move this here. and white got checkmate, white wins. You have the options to either rematch. We'll go ahead and do that one for now. You can rematch. It draws a new board, like so. And then over here in the menu option, you can either resume the game at any position, like that, or you can forfeit the game. And when you forfeit the game, whichever player's turn it is the player who considered the forfeit. So what in that scenario, white wins, and we can go back to the main menu. Okay, so now let's take a quick look at some of these boards. So when you click on these are theme packages. Now when you start a game, it'll have different themes, and that's the idea behind the user interface for the local games and for the menus and everything like that. So now let's take a look at a game against the AI. Okay, so when you first select the player versus AI option, it allows you to select which pieces you'll play as. And so we'll go ahead and select the white pieces and play against our AI playing the black pieces. So we'll go ahead and put the AI in check. As you can see, it responds to the check properly. It blocks with the pawn. That way it can understand checks. It can understand when it's under attack and how to avoid being checkmated. And it has the option to take our queen, so it takes our queen because it's a very high value piece, and it puts it in a big advantage. So let's go ahead and keep making some moves and see how it responds. It's taking our bishop there. And then we'll just play some random moves and see how it responds. It puts us in check here, which is good to do. Another priority that the AI will take into consideration is the ability to put the other player into check. It's an attack on the king, which is the most valuable piece. So it is a priority that's seen as relatively high for the AI. And we'll just go ahead and play some moves. Our AI is not a super high level AI. It's relatively beginner for an AI, but that allows for users of all skill levels to play against it. And we'll go ahead and start making some final moves here. So that's the idea behind our AI and how it works.